Hey, welcome back, everyone. Today we're going to continue our look at the error of truncation and the error of using an approximation in place of a polynomial. And this might be a long one today, so let's go ahead and get started. So we have more context here with Katherine Johnson, and as Katherine Johnson prepares to launch John Glenn into space, we're going to pretend that they're going to use a second ordered polynomial to estimate the amount of thrust needed to reorient the Mercury capsule for re-entry. If they're wrong and either over or under rotate the capsule, the insulated surfaces of the capsule will be subject to the intense heat of re-entry. And goodbye, John Glenn. In something like this, fictional, obviously, this does have its roots in an actual event because John Glenn actually refused to go into space unless Katherine Johnson rechecked all of the calculations, by hand without a computer, just going ahead and crunching the numbers on paper. So there is something to be said here about, Katherine Johnson and, using these polynomials. So going back into fiction, we're going to use a second-ordered polynomial, P2, which is 2 minus 3x plus 1/2 x squared, to estimate the thrust function, f of x, currently an unknown function, which is typical of this. We don't necessarily have to know the function. So we're going to use our polynomial to give an estimate for f of 1.2, assuming that 1.2 seconds is in the interval of convergence for P2. So firstly, what is f of 1.2? Well, I got that to be negative 0.88. How good is that estimate? In order to find out how good this estimate is, we're actually going to need more information. We're going to need to know more about the function that we are estimating. So P2 is a truncated form of an infinite series. Truncated means that we have left off a bunch of terms. We're only using the first 3 terms in this case. So it's a truncated from the infinite series, and the infinite series is exactly equal to f of x. The error of truncation is going to be related to those terms that we truncated. The terms that we left off of the polynomial are going to be very important to the truncation error. So here's a general Taylor polynomial again. We're using the constants c and a as the center of the polynomial. And we use a second-ordered Taylor polynomial, which means that all of those terms in the brackets, I'll highlight them for you. All these terms in green, they were left off of the polynomial. So they were truncated. And what we're going to do is those green terms, we're going to replace them with with something called R2x. So R2x that we've highlighted here, that's taking the place of all of the terms that we left off. They are equal to each other. And if we decide not to use R2, let's say we take that off, then we get an approximation of the function. Now we've been kind of doing that already, just without talking about it, but I want you to appreciate the difference that if you have the infinite series, you have an exact equality. But if you have the polynomial, if you leave off that remainder, then you create an approximation. So look at that. The truncation error, the difference between the actual and the approximation, is exactly equal to the sum of all of the terms that we left off, which we're calling R2. Now, less obvious is that R2 can be, how do I say this? If the terms of a series are getting smaller and smaller and smaller, then in R2, the biggest term should be the third degree term. So if I look at the third degree term that's going to be, at least as big as the rest of the terms. In fact, we could say that at some point, if I'd evaluate the derivative someplace, then the third ordered term is going to be exactly equal to the remainder. And that's what we're saying here in the highlighted section that we have here. The remainder is equal to the next term that was left off of the polynomial. So if we have a second degree term, the remainder for that second degree term is going to be equal to the third degree term evaluated somewhere. That's not completely obvious. In our example, we used P2, so a second degree polynomial. So R2, the remainder of the second degree polynomial, is equal to the third derivative evaluated somewhere over 3 factorial multiplied by x to the third power. And that's, for some reason, that tends to freak out a lot of students. Going back to the example we had, we evaluated our polynomial at 1.2. So the remainder for 1.2 is going to be the third derivative evaluated somewhere, I don't know where, but somewhere, over 3 factorial multiplied by 1.2 to the third power. So it is the the third ordered term evaluated, or where the derivative is evaluated somewhere, but everything else is evaluated at 1.2. I think the problem is that we're saying evaluated somewhere, and at this point in your mathematics education, students can't, they can't deal with, well, it's going to be there evaluated somewhere. Students want an exact place, and I can't give you the exact place, and I'm never going to be able to give you the exact place to evaluate that third derivative. And actually, it's not important. But we'll get to that later. Okay, so P1, let's use P1 to evaluate, or to estimate f of 0.1 if f of x is sine x cosine x. And then it says to use a remainder formula, which is that r function, and the graph of the second derivative to get the biggest possible error of truncation. We're going to start by figuring out our derivatives. So f of x is sine x cosine x, and if I substitute 0, I'm going to get 0. The derivative here, well, that's cosine squared x minus sine squared x, and if I substitute 0 here, I get 1. So let's figure out the P1 of x by starting with, what does every first-ordered Taylor polynomial look like? Well, every first-ordered Taylor polynomial is f of 0 plus f prime of 0 multiplied by x. Substituting things here, I get 0 plus 1x. So P1 is just 0 plus x, which is just x. And if I want to use that to evaluate or estimate f of 0.1, I'm just going to get 0.1. So f of x is approximately equal to P1 of x, which is equal to 0.1. Now it's time for us to look at the error. We start by looking at the second derivative. So what is the second derivative of cosine squared x minus, what is the derivative of cosine squared x minus sine squared x? And you can work that out. That's negative 4 sine x multiplied by cosine x. Next thing we're going to do is we're going to use the graph of negative 4 sine x cosine x to figure out the biggest possible value of f double prime of x, absolute value of it. So we put the absolute value of that fourth derivative into our y equals. And here I want to go ahead and set my window equal to center minus the point of estimation to center plus the point of estimation. So if we're estimating 0.1 and the center is 0, I want to set my window from negative 0.1 to positive 0.1. I'm just going to set the x scale to 0.02. That should give me 5 tick marks on either side of the x-axis. And I'm going to leave y min and y max at negative 0.5 and positive 0.5. Let's see what that looks like. So I can see that the derivative, if this is a graph of the second derivative, I can see that the second derivative is greatest either at the far left here or at the far right here. So I'm going to trace, and I'll put negative 0.1. Let's figure out what that is. That is 0.397 for the second derivative, the absolute value of the second derivative. And then let's also check at positive 0.1. Same thing, 0.397. So this is symmetric. The biggest value of that second derivative is 0.397. Okay, now that we know that the biggest value of the derivative is 0.39733, we can figure out the maximum value of the remainder. And that's the important part here, not the actual value, although it would be nice to know the actual value. In practice, you wouldn't know the actual value, but you can give an estimation for the maximum value of that error. That's the important part. What is the maximum that this error could be? So looking at this, we have it's going to be the maximum of the second derivative. And then we're going to do the rest of the second ordered term from a Taylor series. So divide by 2 factorial and multiply by 0.1 minus 0 squared. Remember that 0.1 came about because that's the x value for which we're estimating our function. And when I evaluate that, I get 0.00198. In other words, this estimate is accurate to the 100th place, because that's where the last 0 is, at the 100th place. So all of that sounds great. If you can deal with everything that we just did, then this error stuff is going to be really easy. In practicality, there are problems because you don't actually have the equation for f double prime. And if you did have the equation for f double prime, then you probably wouldn't be using a polynomial. Except in that case in the 1950s where there weren't calculators, but that's historical. We couldn't figure out the exact error, and we don't really need to figure out the exact error. We just need to figure out the biggest that error could be. Rather, it's more important for us to do quick calculations to figure out the maximum value of the error rather than do a lot of tedious calculations to find the actual error. It's okay for us to, in most cases, to know how big the error could be. And I know that that's kind of weird for people. So we're going to look at 2 different kinds of errors. And the first one that we're going to look at is the general error of truncation. So this is a mathematician that we're going to look at who is Joseph Louis Lagrange. Lagrange was an Italian mathematician with a very French name. And he succeeded Euler as the director of mathematics at the Prussian Academy of Sciences in Berlin. So if you're going to be Euler's successor, you better be on it because you've got some, big shoes to fill. Anyways, the theorem and the error that we know is called the Lagrange error, and it says that the remainder, the error, is always less than the maximum of the derivative multiplied by the place that we're estimating minus the center to the n plus 1th power over the n plus 1th factorial. That's called the Lagrange error bound. And if that sounds familiar, it's because we just did a Lagrange error bound. All you really need to figure out the Lagrange error bound is the maximum value of that derivative. Now, depending on where you place that maximum value, your Lagrange error bound could be bigger or smaller. Academically and in the AP test, you will be led to a number for that maximum derivative. So look out for it, especially if you ever need to estimate the Lagrange error bound or give a value for the Lagrange error bound. You will find someplace in the problem that is the maximum value of the derivative. So that said, let's take a look at our problem here. Suppose that the amount of fuel in kilograms needed to rotate the capsule x radians is given by the function g. And we know some things about the g function. We know that g of 1 is equal to 0.4. We know g prime of 1 is 0.2. G double prime of 1 is equal to negative 0.66. And furthermore, we know that the third derivative of g is always less than 20 for any value of x. So, first of all, let's use a second-ordered Taylor polynomial centered at 1 to estimate g of 0.9. Then, we're going to give an error bound for that approximation. Now, this is a very typical problem that you would see on, a test. It gives you derivatives. It gives you a bound for a derivative. And that bounded derivative is a third-ordered derivative, and we want a second-ordered Taylor polynomial. So that's incredibly typical. So let's go ahead and just do this. Let's write down the second-ordered Taylor polynomial for any function. Okay, so this any second-ordered Taylor polynomial called g will be gc plus g prime of c multiplied by x minus c plus half of g double prime c multiplied by x minus c squared. We're told that the center of this polynomial is going to be 1. So we'll just substitute 1 for c. And then furthermore, we have values for g1, g prime 1, and g double prime 1. So we'll substitute those in now. And then we'll just go ahead and clean up a few of those multiplications and clean up the algebra to create our second-ordered Taylor polynomial. Okay, that wasn't difficult. We've got 0.4 plus 0.2 x minus 1 minus 0.33 x minus 1 squared. The next step is to estimate g of 0.91, and the estimate of g of 0.91 is polynomial 2, evaluated at 0.91. And I'm getting 0.37932. Okay, now for the error part of this. We're going to use the Lagrange error bound. And the first thing that we need on our numerator is going to be the bound, the biggest value of the derivative. Now we have a second-ordered Taylor polynomial, so we need to find the biggest possible value for the third derivative, which luckily for us, they tell us that the biggest possible value of the third derivative is 20. Now remember what I said. They're always going to, in an academic problem, if you're meant to use a Lagrange formula for error, they're always going to give you the biggest value of the derivative in some way. Maybe not as directly as this, but somehow they're going to have to tell you the biggest value of the derivative that they want you to use. So we'll put 20 in the numerator as our maximum value of the third derivative. Now the denominator of this needs to be the third factorial because we're using a second-ordered polynomial. The very next term is a third-ordered polynomial, which comes with a 3 factorial. Now as for what we're going to cube, we're going to use the x value that we're estimating minus the center. Just like what we would do if we were using this third-ordered term in our polynomial. Okay, so I think we have something we can evaluate now. Let's go ahead and put that in our calculator. And we get 0.00243. Now what that says to me is that my estimate is at most 0.002 away from the actual value of g of 0.91. So g of 0.91 at most is going to be, it's going to be 0.37932 plus the error, which was 00243. And the smallest it could be is our estimate minus the error. So this gives us a range of values that g of 0.9 could be. You simplify that and you get that g of 0.91 has to be between 0.37689 and 0.38175. Which brings us to our follow-up questions here. Is it possible for the amount of fuel needed to rotate the capsule 0.91 radians, could it be 0.389? Well, let's compare. Where is 0.389 with this interval? 389. And actually, I think that's a little bit of a mistake. We mean 0.38 and 0.37. So let's check 0.38. Does 0.38 fall into our interval? And yes, 0.38 is between 0.376 and 0.381. So 0.38 is a plausible value for the g of 0.91. Now look how this is different if we try to do this with 0.37. If we try to put the 0.37 in there for 0.91, we create a false statement. So because our statement is false, 0.37 is not a plausible value for g of 0.91. Based on our calculations, only values between 0.37689 and 0.38175 are plausible values for our function g evaluated at 0.91. Man, I really like that exercise. Okay, let's move on. Now, if we know that the polynomial is an alternating series, actually the calculation of error gets a little bit easier. And it gets easier because the alternating series error basically says that the first unused term in all of its glory is going to be the error of truncation. Okay? You don't have to calculate any derivatives. You don't have to multiply anything. It's just the very next unused term, basically. So let's take a look at this problem over here. We're going to construct a second-ordered Taylor polynomial for b centered at 1. So let's go ahead and do that. We start off with the second-ordered Taylor polynomial for any b at any center, and then we substitute our center. And then we're going to substitute the values for our derivatives. And then we're going to simplify. And that gives us our polynomial P2. It's 4 plus 4 quantity x minus 1 plus a quantity of x minus 1 squared. Now part B says to use the polynomial to approximate b of 0.9. So b of 0.9 is approximately equal to P2 of 0.9. We substitute 0.9 into the polynomial, and we get that b of 0.9 is approximately equal to 3.61. Directions for part C are to find the maximum error for our approximation in part B, and then based on that maximum error, we're going to give an interval of possible values for b of 0.9. So we didn't write everything out, and maybe we should, because it says we're supposed to notice that we created an alternating series. Let's take a close look at the terms of the series for P2. And yeah, those terms did alternate, 0.4 minus 0.1 plus 0.01. That tells me that in order to figure out the error, I just need to look at the first term that was left off of, or the next term that was left off of the series, which means I should look at P3 of 0.9. Putting in that third ordered term gives me 8 over 3 factorial 0.9 minus 1 cubed. So the error for the alternating second ordered polynomial is the third ordered term, the very term that we left off of the polynomial. In other words, this term. So the error is going to be, what is that, 8 over 6 times negative 0.1 cubed. So that's 0.00133. Now, in order to create this interval, we're going to take our estimation plus the error and the estimation minus the error. So the actual error, or the actual value of b, evaluated at 0.9, has to be somewhere between 3.60867 and 3.61133. It's a pretty small margin over there. So that tells me that even using 3 terms, a second ordered polynomial, we got ourselves a pretty good approximation. So for the important ideas, technically the Lagrange error bound is an error bound that works for every series, whether it's alternating or whether it's not alternating. But in practice, we're only going to use the Lagrange error bound for series that are not alternating. Now, the Lagrange error bound is the very next term in the Taylor series, with the only exception being that we're going to be using the maximum value of the derivative rather than the derivative evaluated at the center. For alternating series, it gets even easier because the error is exactly, the error bound is the very next unused term. So for me, when I'm supposed to do a alternating series bound and it asks me for, let's say, a third degree Taylor polynomial, I'll always write down the fourth ordered Taylor polynomial so I can take that fourth ordered term and use it for the error. Now you want to be careful because you don't want that fourth ordered term to be part of your answer for the third ordered polynomial. But you really should be cognizant of that fourth ordered term is going to be used as the error. So let's check our understanding. We have ourselves right here a function, and we're supposed to find the second ordered Taylor polynomial. So we're going to need 2 derivatives in order to figure out our polynomial. Firstly, we're going to write the first 2 derivatives. Then we're going to evaluate all of our derivatives at the center, which is x equals 0. Next, we write down the Taylor polynomial for any second degree polynomial named f. Substitute the center, substitute derivatives, and then simplify. And that finishes out part A. Part B, we're going to use this polynomial to estimate f of 0.25. So let's go ahead and substitute 0.25. Okay, so f of 0.25 is 0.1825 just through the substitution. Now the next step here is to use a Lagrange error bound to show that f of 0.25 cannot equal 0.9. So we're going to need the third derivative. And I'm getting that the third derivative is negative 6 over 1 plus x to 1 over 1 plus x to the 4th power. I'm going to take that derivative and put it into y equals. Check my window. And my center of my polynomial was 0. and I'm estimating 0.25. So 0 minus 0.25 is negative 0.25, and 0 plus 0.25 is positive 0.25. Let's keep that scale at 0.05, so I'll get 5 tick marks to the left and to the right. I guess I don't need it all the way down to 0. Actually, I'm sorry. Let's go back here, because we need to find the absolute value of this, because we want to find the absolute error. So let's put this in absolute values. Let's see if I can do this. Okay, now we have it in absolute values. We have our window, so I'm going to push graph. And let's find out where that maximum derivative is going to be. And wow. It looks to me that I didn't make my window tall enough. So let's change our maximum here. Rather than going to 0.5, let's make our maximum 5. Let's see if this does anything for us. And yeah, I'm guessing that I need to go a little taller than 5. So let's go a little taller than 5. Let's move this all the way to 20. And I think my XY scale, I need to turn that into 1 again. Let's see. There we go. So it looks to me like the biggest value of the derivative occurs at negative 0.25. So I'm going to trace, and I'm going to put my cursor at negative 0.25. And then I have here the maximum value of the derivative is 18.96. Let's make that an even, I want to make it 20. So let's make it 20, because 20 is above 18.96. 19 is a prime number. I don't think we're going to have... Oh, you know what? Let's make it 19. So our maximum derivative, our derivative, is always less than 19 in the interval from negative 0.25 to positive 0.25. So the maximum of my third derivative is 19. Now the Lagrange error formula says that the error is going to be less than the maximum of the third derivative over 3 factorial, because we had a second-ordered polynomial, multiplied by 0.25 minus 0 to the third power, because we're evaluating our polynomial at 0.25, and the center of our polynomial is 0. We know our maximum is 19, so now we just need to simplify. My error is less than 0.04947. The last part here is to show that f of 0.25 cannot be equal to 0.9. Coming back down, my estimate was 0.8125. From our discussion of error, we know that the actual value of f of 0.25 has to be less than my polynomial approximation plus my error. And 0.8125 plus 0.4947 is 0.86. And since 0.9 is greater than 0.86, we know that f of 2.5 cannot equal 0.9. 0.9 is not in the range of values that f of 0.25 can be. So that's it for us. This was another pretty long one because we had a lot to discuss about error. If you keep it simple, you should be okay here. I'm not going to lie to you. This is an area which a lot of students have trouble with. But keep it to, the simple parts of this. The error of an alternating series, Very easy, just the very next unused term. And then the Lagrange error is just kind of like the next unused term with a couple of adjustments. So you'll need a lot of practice for this for sure. And hopefully we've given you enough homework to help out with that. So with that, this is the end of it, chapter 10. So good luck, and I'll see you guys next time.